Designing a shell and tube heat exchanger by hand on Excel platform can be a tough job, but it's worth. By performing manual calculations, you can gain valuable insights into how different design parameters affect the equipment's performance. In this tutorial, I'll guide you through Kern's method for designing a shell and tube heat exchanger step by step. Don't worry, I have simplified the entire process with my own Excel add-in, which you can download for free from the video description. Hi, this is Process Guru. Welcome to my YouTube channel. If you find my videos helpful, don't forget to subscribe. To illustrate Kern's method, I'll use the example from Gavin Towler's book. Without any more delay, let's proceed to the example. I'm going to show you the step-by-step method of how to design shell and tube heat exchanger using Kern's method. For this purpose, we have taken the example number 19.1 from the Gavin Towler's book. I have been using second edition. Here we need to design a shell and tube heat exchanger for some process requirement, and the process requirement is like this. We need to cool down the methanol condensate that is coming out of methanol condenser from 95 degrees centigrade to 40 degrees centigrade, and for the design purpose we need to take the flow rate of methanol as 100,000 kg per hour. As a cold fluid, we would be using brackish water, and its temperature would rise from 25 degrees centigrade to 40 degrees centigrade. Here the flow rate of brackish water is not given to us, so we need to back calculate. So as any good practice, we need to start with the summary of inputs that are already available with us. So we have prepared this kind of table of hot fluid and cold fluid. So in hot fluid is a methanol condensate, and the cold fluid is a brackish water. The mass flow rate is known to us, inlet temperature, outlet temperature, allowable pressure drop, though it's not given to us, but we need to have some reasonable number for the pressure drop, because in heat exchanger design, this is very important aspect, like how much pressure drop that we can tolerate in any side, any shell side or tube side. So for hot fluid methanol condensate, we are taking the allowable pressure drop of 0.8 bar. Very similar way, for brackish water, we don't have mass flow rate, so we would require to back calculate this mass flow rate. We know the inlet temperature, outlet temperature. For pressure drop, we are taking some reasonable value of 0.8 bar, and the fouling resistance for methanol condensate and brackish water, that we need to select some reasonable value from the table. So we have a dedicated table on this fouling factors. So I'm just going there. So if you click this, you will get to this fouling resistance tab. So methanol condensate, so here is a fouling factor, and for methanol condensate we can easily take organic liquids, so we can go with the 0.0002 as a fouling factor. And for brackish water, it is not exactly seawater, but it is having good amount of dissolved solids, so we would take seawater fouling factor. We are going with 0.0003 as a fouling factor. Now coming back here, so another information that also needs to be known is physical properties. So here the methanol condensate and brackish water important physical properties are highlighted: the CP, specific heat, viscosity, thermal conductivity, and density. Ideally, we need to take these properties at the average temperature. Average temperature, I mean to say average temperature of inlet and outlet of that particular fluid. Now we will follow this algorithm step by step to design our heat exchanger. So starting with the step 1. So step 1 is about defining the duty as well as doing the energy balance if needed to calculate unspecified flow rates or temperatures. So in our case, we don't know the flow rate of brackish water. We also need to calculate the duty. So first, starting with the heat load. So heat load is very simple formula, mCp delta T. So that is calculated. And once the heat load is known to us, we can back calculate how much cold fluid flow rate is required using same Q is equal to mCp delta T, where Q is known to us but M is unknown, so M is calculated in kg per second and kg per hour. Now coming to the step number 2. The step number 2 is about collect the physical properties. We have already calculated all the properties that are required in the input summary table itself. So we are already done. So now coming to the step number 3. So here we need to assume the value of overall coefficient. It is overall heat transfer coefficient. As you know, the heat exchanger design is an iterative procedure, and this procedure starts with some reasonably assumed value of overall heat transfer coefficient. But how to know that what is the reasonable value of overall heat transfer coefficient? So this value typically depends upon the system. For example, in our case it is like methanol condensate and brackish water system. So what would be the reasonable value? For that we have a dedicated nomograph. Just clicking this. Now here what you are seeing is the nomograph, where in one axis you are seeing the process fluid, and on another axis we have the service fluid. So in our case, process fluid is our methanol condensate, and our service fluid is a brackish water. So by figuring out what is the most relevant category, like here I'm just taking the condensate organic vapor as representing our methanol condensate, and here the river or well sea water as a brackish water representative. When you make the tie line between these 2 points, whatever intersection that you get on the axis of this estimated overall coefficient, that you can easily take as a assumed value of overall heat transfer coefficient. So as per the textbook, I am just taking 600 watt per meter square degree centigrade as our reasonable first guess. Coming to the calculation sheet, so here I have just plugged this value of 600 as an overall heat transfer coefficient. Now coming to the step number 4. Here we need to decide the number of shell and tube passes. We need to calculate LMTD, logarithmic mean temperature difference. We also need to calculate the correction factor in case of multiple tube passes, and we need to calculate the delta Tm, which is a true temperature difference. So coming here, step 4, calculation of LMTD, very simple. Perhaps all of us know how to calculate for the counter current flow. So LMTD is calculated. At this point, we make a design decision about the shell and tube passes. So we just want to go with the one shell pass and two tube passes. And whenever we have multiple pass system, there is always some deviation from the true counter current. So to take care of that deviation from the true counter current, we introduce this correction factor Ft. And using this correction factor Ft, we actually calculate true temperature difference. So delta Tm. So delta Tm is just the multiplication of correction factor Ft and LMTD. So here I have just put here like the shell passes, it's 1. Number of tube passes, we can have one tube pass, we can have any even number of tube passes also, 2, 4, 6, and 8. So presently we are just going with the 2 tube passes. Now perhaps you may be already knowing that Ft, correction factor, the dedicated graphs are available, but instead of going to that cumbersome way of retrieving information about Ft, we will go with this formula of calculation of F without use of graph. So this formula I have taken from the book by Stephen Hall. It's Rules of Thumb for Chemical Engineers, and here by using this formula we can easily calculate what is the Ft, means the correction factor. So there are multiple parameters that we need to calculate, P and R. So formulas are already embedded here, W and S, and finally we calculate F. So if there is any special case where R becomes 1, then this formula here like S becomes like infinite. 1 minus 1 is 0, so 0 in the denominator, it makes this whole term infinite. So we won't be able to calculate this using this way. So there is also for special case R is equal to 1, we need to use this particular formula, and this way we need to calculate true temperature difference. By the way, I have already coded all these things in our Excel sheet. So once you get this Excel sheet, you can review this. It's very simple. So here the true temperature difference is calculated. So we are done with step number 4. Now coming to the step number 5. In step number 5, we need to determine the heat transfer area that is required based on whatever we have calculated so far. So we know the heat load we know the assumed overall heat transfer coefficient. We also know this true temperature difference. So we can easily calculate our first guess about area that is required for the given heat transfer. So this area is calculated. It is provisional area. So temporarily we would believe that this is our requirement. We would do detailing about the geometry of heat exchanger, and we will cross check or we will validate whether this area is sufficient for our required heat duty or not. So now coming to the step number 6. Here we need to decide about the fluid allocation, tube size, tube pitch, and tube material. So here we need to decide like which stream would be allocated to tube side and which stream would be allocated to the shell side. Since the cold fluid, that is the brackish water, it is corrosive in nature, we would assign it on the tube side. Regarding the tube size, typically the tube size would be like 3 by 4 inch or 1 inch in most of the cases. So here as per the textbook, we are going with the 3 by 4 inch. So in metric, the OD of this tube is 20 mm. Tube ID is 16 mm. Tube length, that we are taking a standard length, that is 16 foot. So 16 feet is like in metric it is 4.88 meters. And the tube material that we would be taking is cupronickel as per the textbook. And the tube sheet thickness, we are just assuming it is 25 mm. So this is the tube sheet thickness, and this would actually, these tubes are inserted inside the tube sheet. So that's why the effective length would be somewhat shorter. So to take care of that, we are just deducting this tube sheet thickness from both the sides from the actual length of the tube. So this effective length is coming like 4.83 meters. The tube pitch, we are taking a standard value of 1.25, and we can also make a decision regarding whether we want to go with a triangular pitch or square pitch. So now coming to the step number 7. So here we need to calculate the number of tubes. So for calculating how many number of tubes are required, first we need to calculate what is the area of the single tube. So that is very simple, pi dl. So that is calculated, the area for the single tube. So how many number of tubes are required, that you can easily calculate by dividing the provisional area that we calculated during step 5 by the single tube area. So you get around 954. Here I have used some rounding formula, so I can get the final number in as an even number, so I can divide very easily when we are using 2 tube passes or 4 tube passes. So for that purpose I have rounded up in the multiple of 2. So since we have taken some liberty of making it a multiple of 2, our actual area that we are considering now is like 289.5, which is just slightly higher than this, so it's fine. So now coming to the step number 8. Here we need to calculate the shell diameter. This shell diameter is actually shell inside diameter. So before we go to calculate shell diameter, we need to know how is the tube bundle diameter. So to estimate the tube bundle diameter, there is a dedicated table, empirical formula is there together with one table. So let me show you that first. So it is like this. For triangular pitch, we have this table and this empirical formula. For square pitch, we have this table, which we need to use in this empirical formula. So the same information I have just captured in my Excel sheet. So this is for the triangular pitch for different tube passes, what would be the value of K1 and N1. Very similarly, for the square pitch also we have this table. And here I have put that empirical formula which takes the right value from this table, and we calculate the bundle diameter. Once the tube bundle diameter is decided, we need to estimate, or we need to take the reasonable value of clearance. This clearance is actually in between the tube bundle diameter and the shell inside diameter. For different types of heat exchanger, this clearance requirement would be different. So for example, if your heat exchanger is pull-through kind of heat exchanger, in that case the clearance that is required is higher. So you can easily remove your tube bundle during the maintenance time. But if your heat exchanger is like a fixed tube sheet kind of heat exchanger, then you don't need very high clearance. So for that, to calculate or to take the reasonable value of this clearance, there is a dedicated graph in this given Taurus book. So this is the graph. So you need to read like what is the tube bundle diameter. So we have here like 840.7 mm, and you need to also make a selection or maybe design decision whether you want to go with pull through floating head, split ring, outside packed head, or fixed and U tube. So as per textbook, we would be going for the split ring floating head kind of heat exchanger. So we need to read. So in this step number 8, we need to read this graph. As you know, in Excel, we cannot read the static images, the static graphs. So to allow Excel to read the information of this graph, we need to digitize this graph. So what I have done in my own Excel add-in, TPG Excel add-in, I have added one separate section that is dedicated to heat exchanger design. I think those people who have already watched my earlier videos, they might be already knowing I have used the features of unit conversion and hydraulics in my previous videos. So for this heat exchanger design, we have all the important graphs that are useful for heat exchanger design, like JH factor, JF factor on tube side, JH, JF factor for the shell side, and bundle clearance graph are digitized. So right now we are talking about this bundle clearance graph. So let me click this. So when you click this particular window pops up. So the same graph is shown here. So to produce the graph data in tabular format as a fresh sheet, select the shell bundle clearance button. So we need to click this. So when you click this, the new tab is opened, and what you are seeing here is it is the graph data in tabular format. So maybe let me zoom in. So what you are seeing here is the 3 different types of heat exchangers are shown: fixed tube, split ring, and pull through. And for different bundle diameter, how the clearance changes, that is shown. And here I have developed one small program about here we need to select what is the exchanger type. So for example, in our case it is split ring floating head, it is 2 number. So I have put here 2 number, and now we also need to give the bundle diameter. So bundle diameter, I need to take it from our calculation sheet. So I'm going back to our calculation sheet and linking this cell. Now the information that we need to place there, it is in meter. So I'm just dividing this information by 1000. So we get the clearance. It is 68 mm. So it is just doing all the interpolation, extrapolation, and it will let you know what would be the clearance based on this tabular data. So it is 68 mm clearance. So what I can do here is just link this bundle clearance cell to that Excel sheet. So this is how you can make your Excel sheet very dynamic. So the moment you change your bundle diameter, your bundle clearance would be also updated based on that table, and you can get the updated value of this final calculated value. So here the shell diameter is nothing but your bundle diameter plus your bundle clearance. So it is 908.7 mm. So this is how you can calculate shell diameter. So now coming to the step number 9. Here we need to calculate the tube side heat transfer coefficient. So this is the section, step number 9, tube side heat transfer coefficient. And in this section, we would be using this particular formula. So here in this formula, we require multiple inputs like JH factor need to be known, then Reynolds number, Prandtl number, then viscosity correction factor. For our preliminary calculation, we can safely assume the viscosity correction factor is just 1. There's no impact of this viscosity correction, and we need to calculate this heat transfer coefficient using this formula. So first we need to prepare this Reynolds number, Prandtl number, JH factor. So here just very quickly let me take you through this. So first we calculated tube cross-sectional area, then we calculated, just a second, let me zoom in, then we calculated how many tubes are there in a single pass, then what is the total flow area, then specific heat, viscosity, thermal conductivity, density. If you remember, we have already summarized these things in the input summary table, and those things are just retrieved here. And this is the tube velocity is calculated, then Reynolds number is calculated, then Prandtl number is calculated. There is a L by di. This is the length of the tube divided by inside diameter, has to be calculated because we want to use some JH factor graph. In the JH factor graph, we need to have this L by di and Reynolds number. So for that purpose, we have also calculated this L by di. Now, like very similarly for this bundle clearance, we had to read the graph, but to use it in Excel, we digitized that graph. Very similar way, I tried to digitize that graph of JH factor for tube side. So you need to go to this Excel add-in, TPG Excel add-in, where we have this tube side JH factor. When you click this, you would see the graph. We don't want to read this graph. We just want to translate this graph in a tabular data. So I would just click this one, tube side JH factor table. So separate sheet is generated with all the data for different L by D. Let me zoom in. For different L by D and for different Reynolds number value, what would be the final value of JH factor? So here again, this very similar kind of table we have. We need to plug here Reynolds number, L by D value, and this would calculate this JH tube side. JH factor would be calculated. So Reynolds number. So let me link this with our calculation sheet. So here I'm just in calculation sheet. This is our Reynolds number. Now L by D, that is also there, 302. And now this is the number that we need to use in our formula. So let me link this JH factor with this one. So now your Reynolds number changes, your L by D changes, this JH factor would also be automatically changes. And you would get the updated value of heat transfer coefficient tube side. So I have just used this formula for heat transfer coefficient and calculated this much heat transfer coefficient we can expect on tube side. So now coming to the step number 10. So here we need to decide the baffle spacing and we need to estimate shell side heat transfer coefficient. So this is the section, step number 10, baffle spacing and shell side heat transfer coefficient. So here also we have dedicated formula to estimate the shell side heat transfer coefficient. This formula also requires good amount of inputs like JH factor from the graph, Reynolds number, Prandtl number, then viscosity correction factor. For our preliminary design, we will just assume it as a negligible term, and we also need to have the equivalent diameter. We need to have the thermal conductivity of the fluid. So let me take you through the step by step how we prepare the inputs. So first of all, baffle spacing. So for baffle spacing, there are a couple of rules of thumb, like minimum baffle spacing should be like ds by 5. It is like 1/5 of shell inside diameter of 50 mm, whichever is greater, and maximum baffle spacing is shell inside diameter. So here we would start with 1/5 of the shell inside diameter, and we will go ahead. Then tube pitch is calculated, then cross flow area. So there is a dedicated formula to calculate cross flow area. And equivalent diameter. So equivalent diameter is something that is dependent on tube layout, like it is triangular pitch or it is square pitch. Like we already made this design decision in step number 6, like whether we want to go with triangular pitch or we want to go with square pitch. So accordingly, the formula would be used in that particular cell. So if you choose a square, then the corresponding formula would be used. Right now, let's stay with triangular pitch. And equivalent diameter is calculated. We can calculate velocity also. Then we can calculate Reynolds number, Prandtl number. Baffle cut, you can select anything like 15%, 25%, 40, 45. It's up to you. So I'm just using as per the textbook. I'm just sticking to 25%. But this is important information that you need to use while reading this JH factor graph. So as I said, like here, I have just put the value directly, but we can use the digitized graph to make this value dynamic. So let me show you that the JH factor for the shell side. So shell side JH factor. So we need to read this graph. So where we need to have the Reynolds number, we also need to have this baffle cut, and based on that, we have to estimate what JH factor value we should take. But we will just use the tabular format. I'm just clicking this. So dedicated table is generated. So here Reynolds numbers are there, then baffle cuts are there, and a very similar table input table is there, so we need to plug Reynolds number, Baffle cut, and JH shell side would be calculated. Okay, let me link this Reynolds number with our calculation sheet. So here the Reynolds number is this one. My Baffle cut is 25%, it's here, and we have calculated this JH shell side. So I will just link this value. Okay, so now if we change our Baffle cut, or if our Reynolds number changes, we would see the change in JH factor simultaneously. And now using this formula for the shell side heat transfer coefficient, we can estimate this number. So now coming to the step number 11. So step number 11 is about calculating the overall heat transfer coefficient, including the fouling factors. And this step actually comes with a decision point. So by the end of this step, we need to check how much deviation do we have between calculated value and assumed value. And this deviation should be in the range of 0 to 30%. If this deviation is too high, in that case, we have to revisit our assumed value. So assumed value has to be reassigned to this calculated numbers. We have to again insert the revised number of area. We need to revise our geometry and again do all the calculations to step number 11 and check again this decision point. But if it is yes, then we can move ahead. So let me show you like how our overall heat transfer coefficient comes in step number 11 right now. So this is the formula that we would be using. So here it is shell side heat transfer coefficient, tube side heat transfer coefficient. We have also the fouling factors, and we also need to have the thermal conductivity of the metal tube. So metal tube that we are using is a cupro-nickel. So here is the thermal conductivity that is taken from the textbook. It is 50 watt per meter degree centigrade. Now the reciprocal of overall heat transfer coefficient is calculated using this formula, and inverse of this is overall heat transfer coefficient. The Q is just calculated again, and the decision point is about comparing this assumed value and calculated value, and the percentage deviation that is coming is 24.4, so it is within the range, so we can move ahead. Now coming to the step number 12. Here we need to estimate the tube and shell side pressure drops. So coming to this section here in Excel sheet, the tube side and shell side pressure drop. So on tube side, to calculate this pressure drop, we have a dedicated formula that you can see, and it requires good amount of inputs. One important information that makes this calculation cumbersome is the use of graph, that is JF factor graph. So again, it is also digitized here luckily, so we can use it. And let me directly take you through that JF factor graph, digitized version. So tube side JF factor, so it is tube side JF factor. We need to click it, and so this is the graph. We need to have Reynolds number, and we need to just read this JF factor. So just to make it automated on Excel, we will go for this tabulated version of this graph. So tube side JF factor, it is like Reynolds numbers and JF factors, and we need to provide Reynolds numbers. So let me quickly link this Reynolds number from here. Okay, tube side, I think tube side we did Reynolds number calculation on step number 9. So I'm just linking this one, and we are ready with our JF factor tube side. So let me link this one. Okay, so now it is dynamically linked. So if anything changes, this value also would change. And the delta P is just the formula that is mentioned here is used here, and it is coming 6.8 kilopascal. It's very less. If you remember, like our allowable pressure drop on the tube side is 80 kilopascal. So we have good amount of room to increase the pressure drop if we want by increasing the tube passes, or like that we can do it. But let's stay with this. It's, at least we are not violating the allowable pressure drop criteria. Now coming to the shell side. So for shell side also we have the same kind of graph. So shell side JF factor, and if you click this, you can understand you need to use Reynolds number and the Baffle cuts, and then we need to read this JF factor, but we will make it easy by this table. So here also very similar kind of thing, Reynolds number, Baffle cut, and it would give us shell side JF factor. So coming here, okay, maybe let me use this Reynolds number from the calculation sheet. So Baffle, okay, this one, okay, baffle cut. It is 25, and now we have JF shell side, JF factor shell side. So I just need to link this. Okay, maybe if you want to just reduce the decimals, you can do it. What I'm seeing here is the pressure drop across the shell side is very high, 2.67 bar, and if you remember, our allowable pressure drop on the shell side is 0.8 bar, so we need to do something here. So what we can do, if we want to reduce the shell side pressure drop, the easy way is just to increase the baffle spacing. So let's do that. So right now it is 267 for this much baffle spacing. We have gone for the minimum baffle spacing, but let's say I'm interested to make this baffle spacing 1.2 times. Okay, so that is leading to 159 kilopascal. Okay, we are also seeing our deviation from assumed value is also reducing, so it should not go below 0. And so we still have some room. Instead of 1.2, let me take 1.4 times of minimum baffle spacing. So here we still have some over design, we still have some room, and it is a 103. Okay, that's good, but still we need more, we need to reduce it more. Okay, and here 84 kilopascal. We are at the border. Maybe I can, let me increase it for 290. Okay, we have 15% deviation, and wow, we have now shell side pressure of 70 kilopascal, which is lower than 80 kilopascal, right? So now we are, this is a good design. Now let me summarize this design. Let me tell you one more thing, like, as per this Kern's method, as per this algorithm, you can see after step number 12, we have step number 13 and 14, but they are, step number 13 is like, it's about cost of exchanger. Now, cost of exchanger is something that you can easily plug this information on Aspen process economic analyzer and get to know what is the cost of your heat exchanger. And after producing these numbers, if your management is not very happy, they say like it's too expensive for us. In that case, you have to just go for again, revisit your design to make it a little bit more economical. So from design point of view, like we can stop here now, like step number 12. So we are ready with a design which satisfies your heat transfer requirement. It also satisfies your hydraulic requirement. Hydraulic, I mean to say the pressure drop requirements on both the sides, shell side and tube side. And here, I have just summarized the finalized design of shell and tube heat exchanger. This much is the surface area, this much is the overall heat transfer coefficient, then tube side the configuration, then shell side information, then these are number of tubes. This is like tube side and shell side heat transfer coefficient. This is pressure drop on both the sides. So this is how it's a very lengthy process. It's a very tiring process if you try to do this thing manually. Even on Excel, if you try to do this thing using visually, by reading the graphs, it would be super difficult, or I would say very tedious job. But once you have my Excel edit with you, you can simply use those digitized version of graphs and make your Excel sheet super dynamic. All these digitized versions of the graphs I have provided with this Excel add-in are only for the educational purposes. So before we end this video, I want to show you some useful what-if studies using our Excel model. So one of the biggest advantage of Excel sheet based model is we can now conduct some meaningful what-if scenarios. So let me demonstrate 2-3 cases. So I have just highlighted here like what cases I want to demonstrate to you. One is about tube layout, and baffle cut change, and how the tube passes change, how these things are actually influencing our final design. So let's say whatever design that we have right now, it is a base case. So let me save this. So I'm just copying this and pasting next to it as a static number. Okay, this is our, let me use this same font here. Let me use this as a base case. So we'll just try to have a look like what happens when we change our tube layout from triangular, like you can see in the base case we have a triangular layout, and if we go for square layout, how the other things are changing. So for that, maybe I think it would be easy if I split the screen. So I'm just splitting the screen horizontally. Okay, I don't need vertical split. Okay, so let me keep this here. And okay, in one step, I think step number 6, we decided about what is the tube layout. So instead of triangular, if we go to the square pitch, the square layout, in that case, so what is the common sense tells, or what is the generally known fact, is like the triangular pitch is something which is very compact in nature. So you would end up with a smaller bundle diameter. And when you are having square pitch or square layout, in that case you would be ending up with somewhat larger diameter. So your shell ID would be also increasing. So let's see what happens in our new design. So it is square pitch, here is triangular pitch. If you look at the tube bundle diameter is 0.899 and here it is 0.841. It is some increment is there. Then if you look at the shell ID, it is 969 and here it is 908. Of course, the shell diameter is more. Typically, as the diameter increases, your cost of heat exchange also increases. Okay, so we can see that. We can also see that if the diameter is increasing, so shell side pressure drop is even reduced further. So here in base case, we have 70 kilopascal. Here it is 38 kilopascal. If you look at overall heat transfer coefficient, that is somewhat reduced. Okay, maybe because of less pressure drop, less turbulence. That's why. Okay, interesting. Now let's move to the next one. Let's see what would have happened if we had changed baffle cut. So in base case design, the baffle cut is around 25%. Okay, what would have happened? Let's roll back from square to triangular layout, and the baffle cut is somewhere here. I think it's step number 10. Okay, so instead of 25, actually we should keep it like this because it's input number. So 25%, if we make it 45, then we can see the shell side pressure drop is also relaxed, because now baffle cut is more space is there, so pressure drop is reduced, but this heat transfer coefficient, that is also reduced. So that is, we can understand this from the graph also. So if you look into this add-in and if you go to the shell side JH factor, and you can see like as your baffle cut increases, what happens is your JH factor, it reduces. So your heat transfer coefficient decreases as you increase the baffle cut. That we are seeing here. Other thing is like if you try to look at JF factor, that is about pressure drop. So as you increase your baffle cut from 15 to 45, your JF factor reduces, your pressure drop reduces. So we are also seeing the pressure drop is also reduced from 70 to 46 kilopascal. Yes. Now let's have a look at tube passes. Okay, the tube pass that we have selected in our base case is 2 number of tube passes. Now instead of 2, if we go for 4, what would have happened? Let's see. I think that decision we made in step number 4, right? So 2 tube passes here. So if we change from 2 to 4, so definitely your pressure drop should increase. Let's see what happens. Your pressure drop on tube side, earlier it was only 6.8 kilopascal. Now in this 4 tube pass, it is 47 kilopascal. That's I think that is a good use of available pressure drop that we have done by doing it 2 tube passes. We can see more pressure drop. We are also seeing overall heat transfer coefficient somewhat lower. Okay, that has happened, and shell side pressure drop is also reduced because of, I think I didn't change this 45. Okay, let me roll back from 45 to 25. Where is it? It's here. Okay. Yeah, now we can see that we see some improvement by in overall heat transfer coefficient. If you increase your tube passes from 2 to 4 and all other things are same, in that case you are seeing increased overall heat transfer coefficient. You are also seeing increased pressure drop, but we had good amount of room for accepting the pressure drop, so we are still good with this 4 tube passes. So this is a very interesting tool. You can dynamically change any geometric parameters, and you can get to know how the heat exchanger performance would be affected. You can download my Excel file and Excel add-in from the link mentioned in the video description. If you have found this video helpful, don't forget to like and subscribe my channel. Thanks for watching.